Now, you will notice that most of the questions between numbers 12, 13, up to numbers 22, 23 are just very simple and straightforward. With the solutions I've written here, you'll be able to get those ones. Let's go straight to areas where we have questions on alpha particle decay, beta decay, and all sorts of emissions. Number 24 says a particle loses 8 alpha particles. Number 24 says uranium-238-92 emits 8 alpha particles and 6 beta particles. That you should find the atomic number and mass number of the final product. Now, uranium-38 is 238-92U, as you can see here. Minus 8 alpha particles and minus 6 beta particles. That means you are going to be doing 238U92 minus 8 42HE. This is what represents an alpha particle. HE42 minus 6, 0 minus 1E. That's what represents a beta particle, just like an electron, as I have shown up here around the question number. That means 238. That means the product that we get will be 238.92 minus 842HE minus 60 minus 1E to give AZX, meaning that the mass number and atomic number of our products will be A and Z respectively. Just like ordinary chemical equations must be balanced, nuclear equations too must be balanced. So you get that 238 minus 8 times 4 minus 6 times 0 must give you A. And that gives what? You press your calculator to get the answer there. Also, Z will be equal to 92 minus 8 times 2 minus 6 times minus 1. That gives Z as 82 and A as 206. The same thing happens in number 25, but that's just a uranium atom or a uranium nucleus emitting 1 alpha particle. You get the answer there. In number 26, the emissions are 8 alpha particles and 6 beta particles. Let X be the particle produced. Uranium-238. If it emits 8 alpha particles and 6 beta particles, you do the question the same way and you will get the mass number and atomic number of Z. Now here in 27, let the nucleus produced be M. The mass number and atomic number of M are given as A and Z respectively. So we do the same thing. If X is the atom emitting those, if X is the atom or nucleus emitting those particles, that means the result we get, MAZ, will give us 22688X minus 2 times 0 minus 1E minus 1 times 42HE. That will give us A and also give us Z. You press your calculator to get the final answers. In question 28, X is 2311. That's most likely a sodium atom or nucleus. So that means the mass number is 23 and Z, which is equal to P, the number of protons, is 11. If the mass number is P plus N, number of protons plus neutrons, that means 23 is equal to 11 plus N, and the number of neutrons is 12. As you can see here, you rearrange, you get 12 for the number of neutrons. In question 29, it says sodium-2311 is bombarded with a particle X to give fluorine-29, and what? With the release of an alpha particle. Now, 2311 sodium plus 8ZX will give us 20F9 plus 42HE. Just like ordinary chemical equations, nuclear equations too must balance. So the mass numbers on the left, the sum of all the mass numbers on the left must be equal to the sum of all the mass numbers on the right. So that means 23 plus A must equal 20 plus 4. Similarly, the atomic numbers on the left, 11 and Z, when added must give you 9 plus 2. So that gives you 11 plus Z is equal to 9 plus 2. And that gives what? That gives Z as 0. If Z is 0, that means X is 10X. And that makes X a neutron, because it is a neutron that has these symbolic properties. That means a neutron has no proton. That's why the atomic number is 0, but it has one neutron. So the mass number is 1 and atomic number is 0. In number 30, we go to one part of radioactivity that is called nuclear. We'll go to one part of radioactivity that is called energy emission, or Einstein's law of mass defect. Einstein's law of mass defect states that when an atom disintegrates, emitting several particles, the loss in mass is synonymous to an emission of energy, which is equal to loss in mass times c squared, where c is the speed of light. So that means delta E will be delta m times c squared, or we simply say E is mc squared, where m is the mass lost and c is the speed of light. Here, the loss in mass is 0.5 kg. Speed of light is given as 3 times 10 raised to the power 8 meters per second. Sorry, please. I wrote 3 times 10 raised to the power 3. I should have written 3 times 10 raised to the power 8. So we just compute our numbers. We multiply and we get the energy in joules. The original mass in question 31 is given as 2 times 10 raised to the power minus 5 kg. The loss in mass is 0.3%, meaning that the loss in mass is 0.3 over 100 times 2 times 10 raised to the power minus 5. That gives us 6 times 10 raised to the power minus 8 kg. Using the equation of mass defect, using Einstein's equation of mass defect, or Einstein's law of mass defect, energy produced or released is equal to mass times c squared. That mass is the loss in mass. So that gives us 6 times 10 raised to the power minus 8 kg times 3 times 8, 3 times 10 raised to the power 8 all squared. And if you compute that very well the way I've done it here, you get 5.4 times 10 raised to the power 9. This is very essential. You can see I'm trying to work out my answers using indices. This is very important because when you do an exam like JAMB, UTME, where they don't give you advanced calculators, you have to know how to figure out, working with your indices like this, so that the simple multiplications involving numbers will be easy for you to execute and simplify using your lots of indices knowledge to get your answer. In number 33 is similar. We just find the loss in mass, using the percentage given, and we multiply by c squared. Also, number 34 is also the same thing as number 33. Those ones are just repetitions. But in question 35, there's a different kind of question asked here. It says mass of proton is mp, mass of neutron, okay, 4 protons are brought together to form a nucleus. It says that which of the following equations is correct? Now, what is correct is that the total mass of all the protons brought together, 4 times mp, will be greater than the mass of the nucleus formed, mx, because some of the mass will be lost during collision and fusion, and that mass lost will be, that mass lost will equate to the energy released using the equation E is mc squared, where m is the mass lost, meaning that the total mass of the protons that were brought together or that were fused together to form mx, which is the mass, to form x, which is the nucleus, after fusion, that total mass of the protons will be greater than the mass of x because of some loss of mass during fusion. So we say this is due to the loss of energy during the fusion process. Binding energy, that's another part of radioactivity. Binding energy is the energy that holds a nucleus together, or the energy which holds the nucleons in a nucleus together, or we can call it the energy released when the protons and neutrons of a nucleus are fused. This is also the mass defect of the nucleus, or the energy released when the nucleons were fused, or the energy released when the protons and neutrons in the nucleus were brought together. Binding energy of a nucleus is calculated by finding the loss in mass and multiplying it by c squared, just like I explained just now. So that means delta E, which is the binding energy, will be total mass of protons and neutrons that were brought together minus the mass of the nucleus formed times c squared. So delta M is mass of protons, or the mass of the protons, change in mass or loss in mass, which is referred to as delta M on this left, is the mass of the protons plus the mass of the neutrons that were brought together minus the mass of the nucleus formed. Now, this example says in question 36 now, we are told to find the binding energy when cobalt 59 is produced. Now, cobalt 59 has a mass number of 59 and it has an atomic number of 27. Its mass is 58.9332 U. U is the unit for measuring the masses of nuclides and atoms. The atomic mass of cobalt is given as 58.933 U. 58.9332 U. The mass of a proton is 1.00783 U. The mass of a neutron is 1.00867 U. Now, U is the unified atomic mass unit, which is equivalent to 931 mega electron volt. 1 electron volt is 1.6 times 10 raised to the power minus 19 joules. Now, to calculate the number of protons and neutrons that are present in a nucleus of cobalt, we go ahead and find our n from A is equal to P plus n, meaning that 59 is the mass number and it is equal to the number of protons plus neutrons. Now, P is our atomic number. It's given down below as 27. So P is 27, meaning 59 will be 27 plus n, and our n will be what? 59 minus 27, which gives us 32. Now, this means cobalt 59 has 27 protons. The total mass of the protons will be 27 times MP, which will give 27 times 1.00 times 783 U, and which will give us 27.21141 U. Also, there are 32 neutrons in the cobalt 59 that we are given, which will give 32 times Mn and also give us the total mass in terms of U. So that the total mass of protons plus neutrons present in that cobalt will be 27.21141 atomic mass units, or small letter U, plus 32.27744 U. So now the total mass of those protons and neutrons will be 59.48885 U. This mass is greater than the 58.93320 U, which was given as the mass of the cobalt nucleus formed. So we subtract the mass of the cobalt nucleus formed from the total masses of the protons and neutrons added together. We are going to take 58.93320 from 59.48885 U. So our loss in mass, or mass defect, will be 0.55565 atomic mass unit. That's what I have underlined with 3 different colors here. So loss in mass or mass defect will be 0.55565 U. But 1 U is 931 mega electron volts. So we change the loss in mass, delta M, to mega electron volts by multiplying it by 931 MeV. That gives us our answer in EV. Now, 1 EV is 1.6 times 10 to the power minus 19 joules. So delta E will be equal to this loss in mass in EV times 1.6 times 10 to the power minus 19 joules. That gives us our answer. Number 37 is exactly the same as number 36. It's only that we are dealing with lithium here. We are dealing with lithium 7. There are 3 protons in it and there will be 4 neutrons. So we find the total masses of the protons and neutrons in terms of atomic mass unit, like we did in 36, and subtract the mass of the lithium atom itself, or lithium nucleus itself, from it, like this. So we get our loss in mass, or mass defect, in terms of U, 0.04217 U. So we multiply that loss in mass by c squared. The same way we did number 36, and we'll get the answer. Number 38 says X loses an alpha particle and a beta particle to give Y. It says that we should find the atomic number of Y. So X 84 minus 42He minus 0 minus 1E will give AZ. So Z will be equal to 84 minus 2 minus 1. And that gives us 83. Just a few quick notes here. Nuclear instability versus nuclear stability. What tells you that an atom or a nucleus will be radioactive and unstable? And what makes you think when you see an atom's atomic and mass number rating around it? What tells you that it will be stable and unreactive? What we always remind students of when treating this part of the topic is that they should consider the isotopes of hydrogen. First of all, what are the isotopes of hydrogen? We have the protium, H11, we have the deuterium, H21, and we have the tritium, H31. Now, H31 tritium is radioactive. Why? Because although it's a small atom, the ratio of its neutron to proton will be equal to 2 to 1. And that is much more greater than what? Much more greater than 1. So for small nuclides or for small nucleus, whenever the neutron to proton ratio is greater than 1, the atom will be unstable and it will be radioactive. So that's what happens to tritium, H32, because it has 2 neutrons and 1 proton. So the neutron to proton ratio in it will be 2 to 1. So that's much greater than 1, and it will be radioactive. For very heavy nuclides, like lead, and very heavy metals, and some metals around atomic number 81, 82, 83, and so on. Whenever the neutron to proton ratio is greater than 1.5, the nucleus will be unstable and it will be radioactive. But it will be stable when the neutron to proton ratio is less than or equal to 1.5. This is mostly general for all atoms. Now, what we call a heavy atom or a heavy nucleus is anything that is less than or equal to 20 in atomic number. That's why we said for light nuclides, Z atomic number less than or equal to 20. Unstability. The nuclides are unstable whenever the neutron to proton ratio is less than 1. But whenever the neutron to proton ratio is approximately equal to 1, the nuclides are stable. So we'll be using several examples to explain this later as we move on. All elements with Z greater than 83 are unstable and radioactive. That means all elements with atomic number greater than 83 are unstable and radioactive. Here again, number 39, we have a transmutation equation. These equations are referred to as transmutation equation. Transmutation involves loss or gain of particles by a particular nucleus to form another nucleus, which is referred to as a daughter nucleus. 23Na11 plus a proton. A proton is 11p, gives xpq plus 42he. All we have to do is balance the equation to get our p and q. Number 40 is a simple question like what we have been doing before. You are looking for half-life from decay constant. Number 41, 2, very simple. 42, very simple. 43, very simple also. Just to write the equation and solve for x that you are looking for.